Section 15.2 Transposition matrix. Let's begin with a very simple matrix method, namely the transposition matrix, which is equivalent to the permutation matrix in mathematics. This is a square matrix that has exactly 1, 1 in each row and each column. All the other matrix elements are 0. If you wish to transpose a block of 10 letters, you can do this by treating the block as a row matrix of size 1 by 10 and multiplying it on the right by a transposition matrix of size 10 by 10. The result will be a 1 by 10 matrix with the letters transposed. To move a letter from position 2 in the block to position 5, you would set the element on row 2 in column 5 to 1. Here is an example of a 4 by 4 transposition matrix that changes the message block ABCD to BADC. Transposition matrices by themselves are not particularly practical, but if you have a matrix M that performs a substitution on a block and a transposition matrix T, you can combine them into a single step by using the matrix MT in place of M. That way you get both the substitution and the transposition in a single operation. Section 15.3 The Hill cipher. The earliest cipher based on matrices is the Hill cipher, invented in 1929 by Lester S. Hill of Hunter College and published in the American Mathematical Monthly. A similar cipher had been invented in 1924 by then-teenaged Jack Levine, later of North Carolina State College, and published in 1926 in Flynn's Weekly, a pulp detective magazine. The crypto column in Flynn's was run by M. E. O'Haver, who invented fractionated Morse, section 4.4. Coincidentally, Flynn's Weekly is where Kendall Foster Crossan, also mentioned in section 4.4, published many of his stories. Levine spent his entire career trying to knock down Hill's cipher and promote his own. Hill's cipher operates on the 26-letter alphabet, with the letters numbered from 0 to 25 in some scrambled order. That is, you perform a simple substitution before the matrix operation. You take the plain text letters in blocks of 3. These form a column vector that is a 3 by 1 matrix, P. You multiply this column vector on the left by a 3 by 3 matrix, A, and then add a column vector, B, to get the ciphertext vector, C. In matrix notation, this is written as C equals AP plus B, using addition and multiplication modulo 26. Finally, you convert the numbers back into letters using the same letter-to-number correspondence. Unfortunately, many authors restrict the term Hill cipher to mean a weak, watered-down version of this cipher. To avoid ambiguity, let's number the several versions of the Hill cipher. Hill 0 is the weakest version. You use the standard English alphabet without mixing and omit the B vector so that C equals AP. Hill 1 is somewhat stronger. You still use the unmixed alphabet, but the B vector is non-zero. Hill 2 is the version that Hill originally proposed. You use a mixed alphabet and non-zero B vector. Hill 3 is an even stronger version where you use one mixed alphabet to convert the letters to numbers, but you use a different mixed alphabet to convert the numbers back to letters. This is comparable to the conjugated matrix bifid cipher in section 9.6.1. Hill's cipher, Hill 2, as originally published, was basically a secret method cipher. The conversion of letters to numbers and both matrices A and B were fixed. There was no key. Anyone who knew the method could read the messages as easily as the intended receiver. Most recent books and websites that discuss the Hill cipher ignore the mixed alphabet and concentrate solely on the matrix operations. This would be legitimate if a fixed conversion from letters to numbers were used, because the known mixing of the alphabet could be stripped off. Let's first look at case Hill 0, where A is an unknown n by n matrix, and the vector B is 0, so C equals AP. This is plain old matrix multiplication, which we saw in section 11.3. Reaver can decipher the message by multiplying the ciphertext by the inverse matrix A' of A. The inverse matrix has the property that A'A equals A' equals I, where I is the identity matrix. In the matrix I, every diagonal element is 1, and every other element is 0. The identity matrix is akin to the number 1 in ordinary multiplication, that is, 1 times n equals n times 1 equals n for every number n. With matrices, this translates to IA equals AI equals A for every square matrix A. Emily can also decipher the message if she can determine A'. This B equals 0 version of the Hill cipher is vulnerable to a known plaintext attack. If Emily has n² characters of known plaintext, she can form them into an n by n matrix. Call this matrix P and call the corresponding ciphertext matrix C. Then C equals AP, where C, A and P are all n by n matrices of integers modulo 26. There are several ways to solve this matrix equation. One way is shown in section 15.1.1. If the additive vector B is not all 0, then Emily just needs n more characters of known plaintext, and she can eliminate B from the equation. The extra known plaintext characters can form a column vector P2, and the corresponding ciphertext characters can form a column vector C2. These vectors can be subtracted from the equation like this, brackets C minus C2 equals A brackets P minus P2. This has the same form as C equals AP and is solved the same way, namely by inverting the matrix P minus P2. You subtract an n by 1 column vector from an n by n matrix by subtracting the first element of the vector from each of the elements on the top row of the matrix, subtracting the second element of the vector from each of the elements on the second row of the matrix, and so forth. Suppose that you have no known plaintext. It is still possible to solve the Hill 0 variation. Let's continue assuming a secret 3 by 3 multiplicative matrix C equals AP. Multiplying by A', the inverse of A, gives P equals A' C. In each block of the message, the first plaintext character of the block depends only on the top row of A. That is only 26 cubed, equals 17,576 possibilities, so it's easy to try them all. Each combination for the top row will determine the letters in positions 1, 4, 7 in the plaintext. For each combination, count the letter frequencies. You can compare those letter frequencies to standard English letter frequencies using the tall peaks method described in section 5.9.1. Take those combinations that have the best match, say the top 1% or top 175 combinations. Do the same for the second and third plaintext letters of each block by using the second and third rows of the inverse matrix A'. This gives you 175 plausible combinations for each of the 3 rows. You can now try combinations of these combinations to get possible reconstructions for the entire message. There are only 175 cubed equals 5.36 times 10 to the power 6 combinations to try. The combination for row 1 gives you the first letter in each block. The combination for row 2 gives you the second letter in each block, and the combination for row 3 gives you the third letter in each block. So you have every letter. You can now use trigram frequencies to determine the most plausible plaintext. Use all of the trigrams, not just the 3-letter blocks, but the trigrams spanning blocks as well. This is the same process we used in section 5.10 and section 8.2, so I won't repeat all of the details here. If this fails to produce a satisfactory result, go back to the start and take the top 2% or top 350 combinations for each letter. The Hill cipher Hill 1 with a secret 3x3 multiplicative matrix and a secret 3x1 additive matrix, but with an unmixed alphabet, is rated 3. With a key mixed substitution both before and after the matrix operations, it is rated 5. It can be solved as a general trigram substitution cipher. The rating increases for larger matrices. In order to reach a rating of 10, the matrix must be at least 8 by 8, and the Hill 3 matrix operation must be applied twice. Here are the steps. 1. Convert the message to numeric form using a keyed nonlinear substitution. 2. Multiply each block by the matrix and add the column vector. 3. Perform a second nonlinear substitution on the numbers. 4. Multiply each block by a second matrix and add a second column vector. 5. Convert the result back to letters using a third keyed nonlinear substitution. The two multiplier matrices may be fixed, but the three keys for mixing the alphabets and the two additive column vectors should be changed for every message. Call this cipher double Hill.